So welcome, ladies and gentlemen. I hope you can hear me well. I welcome you to the workshop on simulation in additive manufacturing, ideas for the process of tomorrow, organized by the Technical University of Munich. Within the next 90 minutes, we invite you to journey through different aspects of simulations in additive manufacturing, covering both physics and process applications. We have prepared 4 sessions with experts in their field to discuss laser-based powder bed fusion of metals with Mr. Götz, wire and arc additive manufacturing with Mr. Chow, material extrusion with Dr. Zaremba, and fluid mechanics during the build process with me, Dr. Adami. Our objective in this workshop is first to share our visions for the process of tomorrow, and then discuss the future of additive manufacturing with you. Before we start, a few quick words about the agenda, which already changed right now, but I'll explain in a second. At the beginning, we want to start with a quick movie. I'll broadcast a movie about TUM's Competence Center for Additive Manufacturing. And then we'll right away jump into the discussions on the special topics. Since the group size is actually quite nice for a discussion, we would stay in the plenum all together. We do not need to go into breakout rooms. That was planned for larger numbers, but works even better now. We prepared 4 pitches, short presentations to introduce the 4 mentioned topics. And we'll also have a quick questionnaire, which serves us to get a bit to know you, to know a bit the group, basically, where you're coming from, what is your background, and for each of the topics, what is your knowledge level, what are you interested in? And then we want to enter into lively discussions. Each session shall last about 15 minutes, plus minus a little bit. At the end, we will then have a short summary. We would try to collect a bit the main ideas, and would just really encourage you and invite you to participate actively. You're also allowed to unmute yourself during the discussion sessions, of course, and we're very much looking forward to this workshop. Are there any questions from your side regarding the agenda, technical things, or anything else? You can always use the chat. You can either unmute yourself and speak out loud, or raise your hand in Zoom. There's also this option, whatever you prefer, so that we know there is an issue, a question, or something. Okay, this is not the case at the moment. Then let's start with a short movie. Okay, I just saw that there is no movie, no voice. Actually, it's just a bit of music, but I can relaunch it, and then you get also the nice music. Give me a second. Sorry for that. There you go. Now it should. So there's installation. So practice 2 times, and now okay, can you see it now?
Yes, we can see it.
And then I'll put the animation. Sorry for that.
So great. Thank you for the introduction, Stefan. As you have seen, we have a lot of different manufacturing processes here at the Technical University of Munich. And I would like to start with the laser-based powder bed fusion of metals. Hopefully you can see my screen right now. Is it working? Okay, great. My name is Dominik Götz. I'm a research associate at the Technical University, and I'm working in the field of additive manufacturing. and I'm very pleased to conduct this workshop together with you. And as I already said, I would like to introduce the laser-based powder bed fusion of metals. And the goal is to discuss the need of a process simulation as well as relevant features needed to meet the future challenges within this additive manufacturing process. So starting with the fundamentals, the laser-based powder bed fusion needs a laser which melts the metal powder here in the powder bed, and then the powder bed or the metal powder is solidifying into a solid component afterwards, and then after every single solidification, a new powder layer is applied through a recoater system from a powder reservoir. And then the parts will build up iterative layer by layer on the build platform, so that after all, we have parts with very high, complex and filigree structures and a high surface quality. But the process is also characterized by high process knowledge, and this can be shown here by the two demonstrated parts. For example, we have here a turbo pump coil and very thin-walled blades. So all in all, it can be stated that the laser-based powder bed fusion is a suitable technology for the production of complex components. With the process simulation we are already using, we are able to predict resulting deformations as well as residual stresses, for example. And therefore, we have to take a look at the complete process chain. The process chain can be divided into 5 steps. So at first, we have the building preparation. Here, the components need to be positioned on the build platform. Supports need to be attached if necessary, and also process parameters will be assigned to the part. Then afterwards, the layer-by-layer production will work on the machine itself, so the building process. And after the building process, the parts and the build platform is removed from the machine and going into the next step, the depowdering. Here, the components are depowdered by an excitation with a frequency to remove even the smallest amounts of powder. And afterwards, we have the post-treatments and the post-processing steps, for example, here the thermal heat treatment, the stress relief annealing, for example, and also the mechanical post-processing to prepare functional surface areas. But nevertheless, we are able to predict deformations, residual stresses. We also face different challenges in the context of process simulation. So for example, we have the inhomogeneous microstructure resulting from different geometrically induced cooling rates during the manufacturing process. And these cooling rates are mainly influenced by the assignment of different process parameters, which are assigned within the building preparation, so the pre-processing. Also, the microstructure can transform within the post-treatment. So for example, if we have a stress relief annealing process, we have creep mechanisms which are also resulting in additional deformation. Furthermore, we have also failure due to residual stresses. So parts cannot be used in further applications due to the high temperature gradients, which are then resulting in residual stresses. And also these residual stresses are mainly influenced by the building preparation, so how we select process parameters and where they are assigned. So for example, laser power, scan speed, and exposure patterns. As I already mentioned, the depowdering process is a very important process step to remove even the smallest amount of powder. And also here, cracks can occur during the depowdering when especially eigenfrequencies are hit by the excitation through targeted oscillation. Then the parts can break, and also these parts cannot be used for further applications. And this is why we would like to use the process simulation to improve these challenges and to work on these challenges in future. Last but not least, we have also a big topic, the support structure-free building. Here it is the aim to enable a support-free manufacturing, and therefore a suitable process strategy is needed. So we definitely have to select suitable process parameters within the pre-processing step which are mainly influencing the cooling behavior of the components during the manufacturing process itself. And also there's a benefit for mechanical post-processing. So we have different advantages, for example, higher complexity for geometries that can be manufactured, and also reduced manufacturing time and costs due to the fact that we don't have to remove these support structures after the manufacturing process itself. And now we come to the context of process simulation. We have identified these 4 challenges and now develop different approaches to continuously improve the process by using the process simulation. Here we use a thermomechanical process simulation based on the finite element method, and the goal is to be able to predict both the microstructure, so integrate the relation from mechanical properties and process settings, but we would also like to address the other challenges. So, for example, the failure due to residual stresses when we use a fracture mechanics simulation, the failure due to eigenfrequency excitation by using eigenfrequency simulation, and also the support structure free building, which should be addressed by simulating different process parameters that can be then adapted based on the simulation results, and then also used to control the process, the real manufacturing process itself. But how can we couple these different simulation tools and features? So therefore, we thought about using a digital twin of the production process. The digital twin should then represent the real manufacturing process with all the pre- and the post-processing steps. So all in all, we can summarize the laser-based powder bed fusion of metals has a lot of advantages. So for example, the high complexity and also the high process quality. But however, we still face general challenges. For example, reproducibility and also component testing, which are still required for widespread use. In regard to the process simulation, we would like to use the digital twin to use the most challenging topics, for example, here, the inhomogeneous microstructures, which is complicated for the mechanical dimensioning of the parts. Also the residual stress-induced cracks during the production, which lead to a high reject rate, and also the eigenfrequency excitation, which also leads to the fact that we cannot use these parts for further applications. And all in all, the support structure, we would like to address this as well during our process simulation to enable a higher complexity of the geometries and reduce the manufacturing time and costs. For this, we would like to use the digital twin, and we are sure that this digital twin is able to solve all these problems. And now the question is, are there other problems that we have not addressed up to this point? What are your experiences with applications? What is the need from the industry and also the practical applications? And this is what we would like to discuss after this short presentation now. And also to get a better overview of you, I would like to start with a small poll, which I would like to activate right now. To get an overview, where are you from, what are your positions, what are you working on, and then we can use this as well for the discussion round later on. So hopefully you can see now the poll 1, laser-based powder bed fusion of metals, and I would like you to shortly answer the questions. Also, there are some single choices, multiple choices, and then we can use this for the discussion round later on. So far, I don't see any. Okay, now. Just waiting another 30 seconds. All the answers are coming in. Okay, so another 10 seconds, then I would close the poll. And show the results. So you should now be able to see the results as well. Very interesting. We have a lot of developers which are mainly working on the additive manufacturing process, I guess, as well as research associates. And what I highly appreciate is that, yeah, you think the potential of additive manufacturing is big. So that's why we are also doing this workshop here. We would like you to get familiar with process simulation and also the digital tools we would like to use for a further improvement of the process. So coming back to the question I already asked, maybe which problems have not been addressed up to this point? Are there special issues within the industry, practical applications? Just unmute yourself and yeah, tell us your problems, challenges, or maybe questions. So maybe starting with an easier question. Here at the conference, we have spoken a lot about digitalization the past days. So where do you think we can improve the quality, also the process stability by using tools like process simulation? Is there a need, for example, especially in the manufacturing process itself, or would you say more the post-processing steps? What is your recommendation?
Gregor Eichler here, can you hear me?
Yes, of course.
Yeah, so I, I believe exactly what you've shown in your presentation is completely right, and we need to work on all process steps to make them more digital traceable. The biggest need, I guess, is in the post-process area, as it's still very hands-on and cause a lot of cost per part. So that's why in metal, I would love if the post-processing part would be highly automated and standardized in such a way that we don't have this strong influence on each part, which needs to be post-processed by human. And the work is dirty, the worker is affected through this step. So I would vote for this step to be focused on really as an automated process. But maybe it's not the ideal topic for the digital twin creation, because the others are more suitable to create the digital twin, as those processes are or deliver already data. Yeah.
Thank you for the comment. Maybe an idea what we all also discussed the last days during the in situ measurement during the manufacturing process. We have a lot of in situ monitoring. We have a lot of data we have to handle, and also here simulation can be a tool using artificial intelligence, combining the data with knowledge from engineers, and then also improving the process itself. Are there some specific applications, for example, where you already use kind of artificial intelligence to improve the stability, reproducibility, or also other challenges that you are facing at the moment?
So if nobody says something, I'll just continue.
Yeah, of course.
I know, for example, that serial processes like dental and hearing aids, they have their process chains partly already somehow digitized, especially for the step of quality assurance of the final product. So taking pictures or scans of the products and matching them with the initial CAD file is something what is state of the art if it comes to serial applications like dental and some others. And I believe that this is as well very useful for the business case of spare parts on demand.
Okay. Yeah, thank you. That's what I can also agree totally. We have a lot of different industry. For example, dental industry has other requirements than the aerospace industry. And here, for this reason, we definitely have to maybe also not completely standardize the simulation tool regarding the manufacturing process. I think it'll be also necessary to have specific solutions for different industries, because everywhere are other problems, challenges, and maybe here we can also use simulation tools to cover these challenges in future. But as I already have seen, we are at the limit of this session already. I would like to hand over to Dr. Adami. Thank you for listening to the session, and later on we will give a short summary. Oh, I already see there's a question in the chat. How the digital twin solve an anisotropic characteristics? So maybe short answering this question. Within the process, we have inhomogeneous microstructure, and for example, you can couple the material properties also with the laser strategies, the cooling rates that are occurring during the manufacturing process by using this process simulation. And due to this coupling, we would also be able to address the anisotropic characteristics during the process, and then hopefully being able to have or to be able to use this knowledge to design geometries differently. For example, have higher stiffness in region 1 and have then a lower stiffness in region 2, so that we can also use the process simulation for the topology design and the geometrical design for additive manufactured parts. So thank you very much for the questions. I've seen there are some more in the chat, but maybe we can also answer them afterwards. If you have my contact data, just write me an email and we can keep in contact. Thank you very much.
Well, then let's move on to the next topic. Now we wanted to have a glimpse on the fluid mechanics during the build process, and in particular on the usage of CFD for this step. And again, I want to start with a quick poll. Don't be surprised, the first questions are actually identical. You can just maybe skip them and just continue with questions 3 and the following. I hope you can see the poll, because, okay, now I see answers coming in. Okay, maybe I take another 30 seconds to get some more replies. I see at the moment 27% only. Maybe I can motivate some more people to join the questionnaire. So now let's start the last 10 seconds, last call, like in a pub. Don't forget the 50%. Come on. Okay, almost. One is missing for the 50. And anyway. So you should also see the replies. So again, well, I think what I see quickly, the group didn't change so much. Yeah, what I wanted to see, and it's quite interesting, so that you're maybe if I may summarize that more on the basic level regarding CFD knowledge. And overall, you are quite biased in your opinion. It's just something to play with. Others are, I think, maybe more trustful, but still have big question marks. So it's actually a quite mixed result. One maybe with a nice majority is CFD and experimental studies need always to work hand in hand. I think that's the minimum takeaway maybe from today. That's actually quite good, interesting. Okay, then let's start. I prepared a quick overview, some images, some impressions. Then again, we want to finish with a short discussion on CFD. So what is CFD? Computational fluid dynamics. We solve the fluid mechanics equations with the computer with different discretization schemes, and want to have actually a digital twin already, a virtual representation of the real physics of the real flow. Today we wanted to focus on the build process of laser-based powder bed fusion. Since there actually fluid mechanics play an essential role and are also quite hard to solve. Why is that? A very quick view on the physics. You have many phenomena that occur at the same time. They occur on different scales. Due to the high energy input, you have phase change. You generate a melt pool, so you have a liquid region. You have a powder region which can move. You have a solid substrate. If you look at thermodynamics, you have convection, because this melt pool is not a static pool. It's really highly in motion. You have surface tension effects. You know, of course, maybe surface tension from water. Here it can be much higher. It's liquid metal. And very interesting is the Marangoni convection. Maybe you know this game of putting a piece of paper on water and then soap on one end, and then it starts moving. The main effect is Marangoni convection, and that's very important here for this process. And to solve this one, you need to consider at least the phase change, the different types, so the solid, the melt, and the gas phase on top of it. It's highly dynamic, so any numerical code or model needs to be capable of handling this. You have high density changes, liquid metal and gas surrounding it, and these are challenging problems for simulations. Looking at the build process, actually all the steps involve fluid mechanics. You can look at it from a macroscopic point of view. If you look at really a build chamber of a 3D printer, you have a gas flow which can either blow out your powder. You want to maybe control it for thermal management and things like that. So we do simulations for the entire build chamber. Here the scales are always different. Here we are on macroscopic level. We are interested in the full chamber. For example, we want to control the vapor plume. For the melting, only the melting, if you look locally, it's really on a much smaller scale. We want to resolve the keyhole or the melt pool where the laser interacts with the melt. And there we want to, for example, make sure, either investigate, understand, or make sure that the keyhole pore formation can be suppressed. Then a little bit bigger is looking at an entire melt pool. We can simulate the tracks where we have, for example, balling. We want to study the stability of these films, of these tracks, and that's what you can simulate. And if you go even further down on the smallest scale, we start looking also at the solidification itself. So we can simulate the growth of crystal. structures, which is then, of course, very important to understand or detect regions for cracking phenomena, where to occur and why. For all of these, there exist models, and I think one of the main challenges and the next steps and what we're working on is finally to couple all of them. Ideally, of course, I understand then a user would like to simulate the full process and still know what's happening on the smallest scale, what is his result, but that's really a big challenge. So for each of the separate problems that we sketched here, there's many more, of course, but looking at each of them, there is solutions already today. And the next step, the future, will be couple all of that and incorporate them as a digital twin, even in the real application, in the real process, to have monitoring and really a priori knowledge about the quality of the results. And for us, a big challenge, actually, and that's what I would like to discuss quickly with you, is even if you have the best model that captures everything, we always have to talk about uncertainties. An experiment is not exact. You mostly don't know exactly your parameters. The materials are characterized, but with uncertainties. And it's really a big challenge to incorporate this into the models and also to get access to that data. I showed you quickly that this is a full multi-scale problem. So we need to either focus on different aspects and keep in mind that you cannot get everything in one bowl. Another thing is spurious physics. If you model, you make assumptions. And that means also that you need to know what these assumptions mean in your results. So sometimes you see effects which are maybe physical or maybe not, and you have to be very careful in analyzing and understanding CFD results. So from our point of view, CFD is not yet a black box tool. You need quite some knowledge to interpret, to post-process properly the results. Of course, we want to improve that so that the schemes are so good that they just provide you the right answer, but honestly, we are not yet there. We want to achieve post-diction capabilities, so not only showing a comparison, working with the models and find it, but we really want to a priori take your settings, simulate it, and really have a match with the outcome, so that you can then use it blindly for development, optimization, and for process steering of your job. And maybe for a manufacturer, one important thing is the first time right standard. That would be solvable probably if you have a digital twin that captures everything well. So what we need to learn and want to improve is how to make users, industry trust the simulations so that you can really use them and replace part of your experimentations. What is to expect also from a CFD? That's maybe information for you or what you are interested. And how can we maybe certify these processes or make sure that we have the same standard everywhere. Maybe I start with a quick question that came in the chat. I think that was during my talk. How do you see production under keyhole mode in order to increase productivity? Sounds like a simple question, but it's challenging. So when you think about increasing productivity, the first thing I would think about would maybe to speed up the laser motion. That would be one way for this process, which would actually help a bit to suppress keyhole mode. But then you get many other problems. If you go to higher laser energies, then yes, of course, you get the keyhole mode. I think it's maybe the keyhole has advantages and also disadvantages. I could imagine of really an amazing phenomenon if you can control it. If you have control of it, then you can even maybe get deeper mixing into the melt pool. This could be beneficial, but of course, it's probably more challenging to make sure that there's no gas pores. So right now, at the moment, we are trying to understand and predict it quantitatively well. so that we understand when it occurs, how to use it then for real productivity improvements. That's one of the next questions. So there's so as long as there's no comment, question, or interaction on the audio, on the voice level, then I would continue discussing maybe the questions coming in the chat. There's another question: if the software would be able to simulate partial pressure of chemical elements to stabilize the keyhole. The software that we used for the keyhole simulation that I showed you here is based on smooth particle hydrodynamics. In that model at the moment, we are not considering different chemical elements. If I understand your question, like mixtures, we assume currently pure elements or pure phases, pure materials as a single phase, and do not track individual elements. But yeah, from a modeling point of view, that would be possible, but it's not currently in the model, in the code. Maybe one question to you. So for those who are using a CFD, what is maybe your approach to make sure that the pictures you're looking at are actually meaningful or the right ones? So do you just blindly trust them, or do you have maybe internally certifications or like cases that you say, okay, I first check this one and then I continue it, or do you use software packages and just trust them? What is the approach there? So again, if I don't get an answer, I want to answer the chat question actually. Okay, there now it's mixing. So I start with answering the chat question, then maybe I continue with my question. There's a question: if our simulation includes the metal vapor jet, gas, and spatter. Partly yes. So what we include is the vapor by effect. So we use a so-called recoil pressure model. So the evaporation is phenomenologically modeled by this depression. The gas phase on top of it is simulated. We can simulate also the thermodynamics, basically the exchange of energies. Spatter, that's one thing that we want to simulate, but there we want to couple it with, for example, DEM, so that the powder phase is movable and would then really be injected. Then you would probably see spatter. If you mean spatter from the melt itself, yes, there you could simulate, or we would see ejections. A nice question about SPH, what the advantages of using SPH since it's less developed as compared to classical finite volume method. Yes, that's true. Finite volume methods are maybe more established. I try to quickly show you the complexity of the multi-physics, multi-scale problem. And if you have phase interfaces like a keyhole with strong deformations that highly dynamically change, most of the finite volume methods I'm aware of have at least challenges, if do not fail. And SPH as a Lagrangian method, where the regions of fluid can freely move, has quite many advantages for this application, and we use it successfully to simulate this problem. Okay, time I think is actually also running, so thank you very much. Also, thanks there was one reply, I think, to my question, what you do internally. There was mentioned that you validated with an experiment. Yeah, that would be interesting for us, actually, if you use literature experiments, or if you have maybe your own experiments, also for an academic research institution, that would be interesting maybe to have some exchange there. So once again, I'd like to invite you for further discussions. You'll find my contact details on the first slide. We'll also share it at the end, maybe again. Thank you very much. And now I hand over to, where is he? There, Dr. Chow.
Thank you, Dr. Adami. I'm not a doctor yet, but thank you for the title. There is a short break planned on the schedule. I don't know, do we need a break of five minutes break, or can we just continue?
I think we can continue. So
okay, all right. Then I will just continue. I wish. Oh, someone said break.
we can also take a short 3 minutes break so that everybody
Okay.
can get a coffee, and then
Okay.
we're back on
150.
150. Yeah, 30.
Yeah, 150. Let's meet back here at 150. All right. Short break for everyone. All right, it is 1:50 p.m. Let's start on time. Good afternoon, ladies and gentlemen. My name is Xiaofan Zhao, and welcome to my session. Just like my colleagues, I'm a research associate at the Technical University of Munich. And in this session, we are going to talk about challenges and simulations related to the wire and arc additive manufacturing technology, or in short, WAM. Now, instead of starting with a poll, I just want to ask the question, how many of you have actually worked with WAM technology, wire and arc additive manufacturing? Maybe you can just raise your hand or do an emoji for me just to see how many of you actually know this technology. Okay, we have one person. Okay. It seems like this technology is not very well known. So yeah, let me first take a minute and explain the functionality of the WAM process. So on the illustration, we see a simplified CAD model of a WAM test station. Here, an industrial robot is holding and guiding the welding torch. A wire, which is not visible in this image, is fed through the black tube next to the industrial robot into the welding torch. And at the tip of the welding torch, the metal wire is swiftly heated up to its melting temperature, and the liquid metal is deposited onto the build plate, where it solidifies to a solid geometry. We have an arc welding process here, so the thermal energy to melt the wire is generated by an electric arc. We guide the welding torch parallel to the build plate while welding. We receive a weld seam, and if we repeat this process layer by layer in a controlled manner, and stacking the weld seams on top of each other, we receive a three-dimensional part. Printable materials are all weldable materials such as steel, aluminum alloys, or also titanium alloys. Yeah, the key advantages of this technology compared to, for example, powder bed fusion is its high deposition rates of up to several kilograms per hour, depending on the material. And in addition, we also are able to produce very large parts, since in theory, we're able to utilize the whole range of the industrial robot. Furthermore, we have a very robust, clean, and material efficient process, since all of the problems related to metal powder become superfluous. In WAM, we use wire primarily, so we do not have to worry about powder contaminations, powder aging, and other powder-related safety concerns. On the center image here, we can see a snowflake printed using steel, and on the right side, we see a T-shape manufactured using a titanium alloy. Here, half of the part has undergone a milling process, which is also a significant step in the WAM process chain. The possible applications of the WAM technology are everywhere where we need large metal parts, such as in the naval industry and also especially in the aerospace industry. Even though WAM is very promising, there are certain challenges we still face for this technology to be viable in a large-scale industrial field. So on this slide, we see the process chain for WAM. We start, like with any other AM process, with a build preparation and a CAD model. Next, we have the process planning step, where the CAD model is translated into the robot trajectory and welding parameters. This step is similar to the slicing process of powder bed fusion parts. And then we arrive at the building process. Subsequently, we have an optional heat treatment step. And finally, we finish with a mechanical post-processing, where relevant surfaces are milled and finished. We have identified some main challenges we face in industrializing WAM, which can each be attributed to certain steps of the process chain. For one, we also have inhomogeneous microstructure. We know that the microstructure significantly determines mechanical properties, and the material is only as strong as its weakest link. Therefore, we have an interest in keeping the microstructure homogeneous and also predictable. During the building process of certain steels, for example, we have large martensite regions on the top layers, but in the lower layers, which have been reheated repeatedly, we have predominantly ferrite regions. So we have a difference in hardness in one part. In order to influence the microstructure, we can also use thermal heat treatments and mechanical post-processing. However, we do wish to know the microstructure inside the part in advance. Next, we have inconsistent layer geometry. Unlike the powder bed fusion process, where powder is melted into microscopic weld seams, we have large melt pools in the WAM process. And as Dr. Adami already said, melt pools are liquid, and there is always a certain randomness in their geometries, which can also be which is also visible here in the final product. And also here we would like to know how a surface is structured before it is built. Another thing are complex geometries, which pose a primary challenge to the build preparation and the process planning step. Similar to powder bed fusion, geometries with overhanging angles are difficult to manufacture. And for example, in order to print the part displayed in this image, we need true 3D printing, where the substrate is placed on a rotary table and the part is also sliced in non-planar layers during during printing. Yeah. So in the WAM process, we need the robot to work together with a rotary table simultaneously. This is already possible, but the automation is still very challenging. So we require better slicers and also robot trajectory generators. Finally, we have thermal warping. During the building process, the process zone is very hot compared to the rest of the part. And due to the temperature differences, we induce thermal stresses, which ultimately result in thermal warpings. During heat treatment, the thermal stresses can be relieved, but the contour accuracy cannot still be guaranteed. Therefore, we would like to know previously to the building projects which deformations exist where in the part in combination with which process parameters. Fortunately, most of these aforementioned challenges can be tackled and also conquered using simulations. The microstructure can be predicted using microstructure simulation based on previous thermal simulations. The layer geometry can be predicted using, for example, CFD and SPH simulations. Complex geometries can be managed using specific post-processors. And the thermal warping, which is a very big problem currently, is addressed using thermomechanical process simulations. The predicted warpings of the simulation can then be adapted, can then be used to adapt the geometry, and it can also be used to choose the optimized welding trajectories. So in summary, we have the WAM process, which is a very promising technology on its own for the production of large volume parts. However, it faces certain challenges such as inconsistent microstructures and also thermal warping. And however, all of these can be addressed using simulations and a digital twin. So as we have seen in this short presentation, the WAM process is very promising. However, the key challenges can exist and can be solved using simulations. Now I want to ask you, perhaps where do you see the key challenges of WAM technology, and if you have and since many of you have not heard about this technology yet, perhaps you can also talk about, possible possible fields where you can apply the WAM technology as well. So okay, I don't see any questions yet. How do you see the development of special alloys specific for WAM? Yes, it's a very interesting topic. Welding, WAM is like, WAM can be thought of welding on top of each other. However, there are differences to traditional welding in the sense of what happens in the process zone. So specific alloys developed for WAM is certainly a very interesting topic and very interesting field, which can be expanded on in the future. Thank you for the question. Yeah, perhaps we can go over to the next presentation from Dr. Zaramba. If you have any questions regarding WAM or WAM simulations, you can reach out to me later. Thank you. Oh.
Okay, yeah, now we are leaving the metal side. We are coming now to the plastic side. What I want to talk about now is extrusion processes, in this case for thermoplastic materials. You see the scheme of the process. On the left side, there's the red area where the thermoplastic material is brought into a melting state. We press the material out of a nozzle. By moving the nozzle a defined way, we build the part track by track, layer by layer. Usually, especially for the small desktop printers, we very often have such heat build plates. You can buy these printers, desktop printers already in electronic shops. What we are going for is actually large-scale printing. The simplicity of this process, actually what this scheme shows, is that we can very easily adapt these components. So we can introduce a bigger extruder. We can take this bigger extruder and adapt it to a robot, very standardized components, which lead to a process equipment, what we can see here in the picture in the middle. This is actually our big printer here in our lab. We can reach here up to 14 kilos per hour material extrusion, which is quite a lot. So that's the reason why we thought going for big parts actually. What you can see here is actually the component we did in a Clean Sky project. It's an aerospace tooling made out of PEEK, short fiber reinforced PEEK. So more or less tool as a component for introducing this 3D printing of plastics into a real application. Another big advantage of this material extrusion with thermoplastic is shown on the right picture, where we are about to integrate continuous fibers to the part. These continuous fibers bring the advantage that we can adapt local material properties to local part requirements, and therefore reach another mechanical performance level, which leads us to structural parts actually. So in general, to summarize that, material extrusion with thermoplastic material is an established process, which has big advantages for large-scale production. So coming to the next slide, which doesn't work, nochmal von Hand. Genau. When you look for the process of building such a part with material extrusion of thermoplastic material, it's more or less according to all main 3D printing processes. We start with a CAD design, for sure, with integrated features for 3D printing. We take this part design, bringing it to process planning. The end of this process planning is more or less machine code, which gives us the possibility, or which is the baseline for printing the part itself. And we end up with a post-processing process, complicated word, like milling here. We at our printer have an integrated milling module, so we can change the head from printing to milling. We use it in two ways. One way is that we just integrate like reference surfaces for further post-processing. For other like milling operation or other stuff you can do, or we mill the complete surface ourselves. It depends actually on the size of the part. Derived by that, next. The typical challenges we are addressing at the moment on our institute are here on the first one is the inner homogeneity of the microstructure. Since we are doing most of the printers actually with plastic material work with short fibers, by extruding these fibers, there is a certain alignment of the fiber, depending on the pressure in the nozzle, depending on the speed, etc., etc., etc. The next one, the next issue we tackle is the porosities, because by printing track by track, for sure there are interfaces, track next to it, the track the track to the substrate, where porosities are happening. There is the adhesion between tracks and sublayers. Issues we need to understand to get a feeling what's actually in the end possible with the part. Next. Next topic, we heard that also in the presentation before, we have certain thermal distortions, especially when you go for big parts. You start printing with a hot material. When the part gets bigger, the first layer starts to cool down. Thermal gradients within the part lead to thermal stresses. These thermal stresses, when they are high enough, they lead to these kind of delaminations, which usually leads to a scrap part, and you need to do it again, actually. The last topic we are going for is real 3D printing. We have already an extruder on a robot, which is a highly flexible machine, which is capable of real 3D movements. And to use the real potential of this technology, we need to go for aligning the fibers in a real load situation in a real 3D way for optimizing the mechanical performance in the end according to the load situation. Next. How do we go for this direction? And for sure, like the others, also we are going for digital twin. These digital twin methods with all these simulation methods are one way how we can solve these issues to predict these material properties, to these requirements, to more or less make this process, develop it further to achieve defined properties in a final part. We go for material to generate kind of a homogeneous defined microstructures. We are simulating the typical extrusion process where the fiber orientation is in the end the outcome, what we can use as for mechanical simulation. Also the temperatures are an input for the layer by layer adhesion topic, which goes for the next porosity, layer to layer adhesion, where you have the crystallinity development when you place the track with a certain temperature on the substrate. This temperature simulation you actually use as an input for the residual stresses which develop during the complete printing process, which leads in the end to prediction of this delamination topic. And the last one is the real 3D printing, where we bring the part requirements to the simulation. We use the load conditions to use the principal stresses as an input for path planning to generate real 3D printing codes, which we use for robot printing. This brings me to the summary. In the end, we're going for 3D printing for large scale parts. We started this process with tooling, building tools for other processes. The big aim or goal for us is also to use this kind of process for structural applications. When we go there, we need to tackle different topics like the microstructure. We need to control the porosity level. We need to control the warpage, the deformation during printing with process simulation. And to go for the highest potential of this kind of process, we want to go for this real 3D printing to bring the fibers actually in the place where we wanted to have it according to load conditions. And with these integrated simulation methods, we do think this is one way how we can bring this process to the next level, and hopefully also for your applications, for example. So now we can start this the rubber, yeah. If there are any questions already, please use the chat. Being patient here is the big effort. So please answer some of the questions. The first questions out of the chat. What do you think about variable flow rates of material at junction points to reduce porosity? For small printers with the filament printing, that's kind of an option. For the big, large scale version, it's getting more complicated because we have, after the typical extruder, we have how's it called in English, a pump, which can control somehow the flow, but actually a typical plastic extruder is kind of not very flexible in changing flow speed. And that's why for reducing porosity, you need to find the sweet spot where you have the lowest porosity. And that's the first step. All other topics are in addition, actually. That's what I think. Yeah, how efficient is actually this non-planar printing, the real 3D printing, is something we do realize here at our research lab at the moment with non-commercial available tools. So let's say the programming itself is not that efficient like a typical board solution, but it's, yeah, you can do it actually. Since you are using kind of a structural simulation as an input, you optimize the part, you get the principal stresses out of it. It's getting kind of, yeah, it's getting more complicated, and therefore it does take more time than a usual process planning actually. But since you are combining these structural simulation with the process planning, you are integrating two steps together, which usually helps actually both sides, the simulation department for the structural simulation and the programming guys, to get in the end a better result of your part. Further questions? Insgesamt. Are there any further questions in the chat? Just to mention that aside, with me is David Collin. He's the one who is doing more or less the work here for this presentation, actually, and he's also one of the guys here doing the simulation topic here. Genau. General questions. Another question in the chat. How do you link the toolpath with the simulation? David, darfst du gerne machen.
I will try to answer this question. So basically, we use a simulation in ANSYS, and then we transfer it to Rhino. And in Rhino, we have the possibility to integrate the result of the principal stresses into the tool path, or the planning of the tool path.
Does it answer your question? Hopefully.
Yes, it does. It was my question. Thank you for the answer. We also have the topic of linking the toolpath with the simulation, but we do it a little bit differently. Perhaps we can talk about it later together.
Sure, always open.
Thank you.
If there is no question in the chat anymore, perhaps you can think about, do you have any applications already? There's another question, okay. Have large nozzle size, how good is the surface quality and how to improve it? Yeah, for sure, when you're having a larger nozzles lead to more roughness, especially when you print just a straight wall. The side surfaces are not that straight. You have got this typical layer by layer surface. And the main topic to improve the surface is milling. Like that's a general issue actually. And so far we work on problems. We have a project actually, for example, where we smoothen the surface by just using a heated ball and locally melt the surface again and press this melted area actually in these gaps in between. It's like ironing just for 3D printing actually. Yeah, question, do you adapt process parameters based on the real 3D geometry to prevent problems? Would be nice to be that far, but that's the way we are aiming for. First of all, we have established this process chain, how we do the 3D printing, the real 3D printing. Now we optimize this kind of way of doing it. We verify it in 3D printed parts. And when we've realized that, then with the next project, we will go for this direction actually. But yeah, I think this is something everybody would like to have. Genau. So in general, a question, the application of, let's say, large-scale printing with plastics, is this a topic? What kind of applications you're going for? Is it, we are using this tooling topic as an enabler? Do you see other, let's say, yeah, ways of bringing 3D printing to a real application? Okay, so I think when all questions are kind of answered, thanks for your time. I hope it was interesting. If you got further interest, don't hesitate to contact us. And please, Dominic, continue.
Yes, exactly. Thank you also for your presentations and thank you all for the discussion. Now we've prepared a short summary showing you the results here from our discussion. As you've seen, we have we gave you a short overview to metal as well as plastic based additive manufacturing processes to give you an insight in simulation and what are the next challenges to use these simulations within a complete workflow within your industry applications and so on. And summarized here, we have the main challenges. So for example, for the laser-based powder bed fusion, we have the inhomogeneous microstructure, residual stress-induced cracks, as well as eigenfrequency excitation during the depowdering step, but also the support structures, which are an enabler for shorter manufacturing times, as well as a higher geometric complexity. And one topic that we discussed here within the workshop, that we also need to standardize the process, especially the post-processing steps. And maybe there's an opportunity for us to implement these post-processing steps more in detail in a standardized way, also in the process simulation, to enable and improve the additive manufacturing process itself. As a second topic, we looked at the fluid mechanics of during the building process. I'm just turning on my laser pointer here. Here the main challenges were uncertainties. We have how can we say that the result of the simulation is true, and how do we have to evaluate this simulation results? Also multi-scale problems, multiphysics, and also spurious physics. How can we implement these different effects in CFD simulation to be able to have good simulation results and also use these results for the improvement of the manufacturing process? One thing that was discussed here is the physical models maybe are more important than phenomenological models, because you were talking about spatters, vaporization, and these are quite complex physical effects that have to be implemented in the simulation, maybe as one of the future challenges. Wire and arc additive manufacturing as also one of the metal-based AM processes. This is also with the inhomogeneous microstructures, inconsistent layer geometry, and also the crude CAM software, so that we are able to plan the different ways how to manufacture these parts, and also then reduce the thermal warping of the parts themselves, reduce deformations, and also know and predict the residual stress inside the geometries. And also one topic that came up here within our workshop was how we can use new materials and, for example, specific alloys to widen the applications and the usage of wire and arc additive manufacturing. At least we've spoken about the material extrusion also here, quite similar to the other processes. We face the microstructure problems as well as the fiber orientations and the porosities in the extruded material. Also here we have the problem with delamination, deformation due to residual stresses, due to the way of how to manufacture the parts. And here we are quite sure that process simulation can be one of the keys to enable a better quality of the process by simulating, modeling the effects, and then predicting the final result before we are printing the parts themselves. So one point here is also another point, the real 3D printing, as well as the last mentioned part, the implementation of process parameters on the real 3D geometry. So hopefully we gave you a short insight into our topics, the ideas for the process of tomorrow, how we would like to improve the additive manufacturing process. And if you have any questions, you can contact us by mail. And therefore, we are going to slide 1, where we have here our contact data and the emails. So if you're interested, let's keep in contact, and we would like to talk to you, keep in contact, and thank you for the participation And we wish you a good day, and maybe we will see next year on a second workshop or also on other conferences and talk about these topics of process simulation in additive manufacturing. Thank you very much. Have a good day.
Danke, ciao.
Bye.
Thank you. Bye bye.